Today, we will discuss a very important topic, which is hidden Markov model. Before that, we would like to draw a perspective around this topic, the topic of hidden Markov model. And this perspective is about what is the role of probability in artificial intelligence. Why is it that probability has started playing an extremely important role in artificial intelligence in recent times, and in particular natural language processing, the field of statistical natural language processing draws immensely from probability and probabilistic techniques. When we were doing part of speech tagging, we had mentioned hidden Markov model, and we had also described how the part of speech tagging problem can be solved by hidden Markov model. We had seen that the part of speech tags are states and the words of a sentence are outputs of this machine, and the states which are traversed of the machine, these sequence of states produce the tag sequence. Now, it is time to delve into the theory of hidden Markov model in the context of natural language processing and artificial intelligence, and we proceed to discuss this. All right. So, the fundamental questions which come in artificial intelligence are with respect to probability are: what is the relationship between AI and probability, which situations need probability, which models are used to model uncertainty. So, these are very basic questions at the foundation of intelligent processing, and we would like to discuss them to an extent of detail. So, a central concern in artificial intelligence is the question of classification. This underlies so many different problems of AI that the whole problem merits a complete and exhaustive studying. Classification divides the data into different classes. Another problem is clustering, which is concerned with like kinds of data being clustered together, being put together. An allied problem is prediction based on previously seen data, make predictions about the new data. This may be a clustering problem or a classification problem, in the sense that the new data may be given an existing class, or it can be put to a particular cluster. So, these tasks are achieved by using mathematical models and selecting features to represent data. Applications of probability are probabilistic planning, natural language processing, expert inference, and scene understanding. What we will do is we will concentrate on NLP and see how probabilistic approaches are not only needed, but are critical. So, this brings us to the question of what are the models of uncertainty. At any point of time, we have partial information about any non-trivial situation. So, this is the key point in any situation which is of any level of seriousness. We have to work with partial information. This is a must, and we also work at levels and layers. This is inevitable. The models which are used for uncertainty processing are fuzzy logic, probability, information theory, non-monotonic logic, and so on and so forth. All these are very important models, each having its own characteristic. Now, the point to note here at this particular slide is the point I am making about working with partial information. We will have umpteen number of examples, but this is an inevitable situation. For any non-trivial task, whenever we are asked to do a particular task, we find that the information that we have to work with is very much partial. So, if we look at examples, we take examples from language processing, and this is because language processing, we are all familiar with this task of language generation and language analysis, and discussing uncertainty in terms of natural language data does not require any sophisticated instrument, but only a sequence of words which need to be pondered upon. So, here I give a situation. The first situation is I went with my friend to the bank to withdraw some money, but was disappointed to find it closed. Okay. So, this is the sentence. I went with my friend to the bank to withdraw some money, but was disappointed to find it closed. Situation 2 is a teacher-student dialogue. This is from Times of India. This is presented as a kind of small joke, but let us look at the language processing issue here. Teacher-student dialogue. Student was absent in the last class. Teacher asks him angrily, "Did you miss the last class?" Student, "No sir, not much." So, we will come back to this example. The whole punchline is based on this particular segment of text, not much. So, we begin to analyze situation 1 and investigate the kind of uncertainties that prevail in situation 1, the sentence. The sentence, you remember, is I went with my friend to the bank to withdraw some money, but was disappointed to find it closed. First ambiguity we are dealing with is part of speech ambiguity. Okay. Part of speech is a well known concept. These are grammatical categories like noun, verb, adjective, adverb, preposition, conjunction, etc., which are assigned to the words in a sentence. Here we find in the sentence the word bank appears. First part of speech ambiguity we meet on this word is that bank can be a noun or verb. The verb meaning of bank is depend. For example, I bank on you, I depend on you, and therefore, bank can be a noun or a verb. Similarly, closed, I found the bank closed. Closed can be a verb or an adjective. The closed bank denotes the bank in a state, and therefore, closed is an adjective. So, it can be verb or adjective. Now, if I ask you what would you assign as the category of bank, I think most of you would say that this is noun, and many times I have seen that this ambiguity is resolved from a very simple surface analysis, where the clue is that bank is preceded by the, bank is preceded by the, and we know that an article can precede only a noun, therefore, bank is noun. So, there could be other clues like how can verb bank be closed, only the noun bank can be closed, or withdrawing money from bank, withdrawing something from a verb does not make sense. Those things are deeper analysis, but one can see that a simple surface clue, if captured, would disambiguate this. So, the other kinds of analysis which are deeper rely on semantics or the meaning content of the text or segments of text. Next kind of ambiguity you would like to look at is sense ambiguity, also known as the word sense disambiguation. Even after we have disambiguated bank in terms of its category, verb or noun, there still remains another uncertainty about what bank do we mean Do we mean the financial institution bank where we deposit money or withdraw money from, or does it mean a river bank or embankment? Okay. So, there is this sense ambiguity which again needs to be resolved, and this is an uncertainty. Similarly, we look at the word withdraw, which means either take away or go away. For example, you could have a sentence where the chairman angrily is saying to somebody, if you cannot remain silent, then withdraw from the meeting. Okay. Or I withdraw from the committee, which means I resign from the committee. So, withdraw also can have multiple meanings like take away, go away, and so on. So, the sense ambiguity resolution in this particular case can be obtained from the clue words money and withdraw. Okay. So, these are very strong indicators that the word bank is being used in the sense of a financial place rather than a river bank. So, this is the issue of sense ambiguity. Then there is this lexical loss ambiguity. Our sentence was, I went with my friend to the bank to withdraw some money, but was disappointed to find it closed. So, you see here this particular segment or clause, but was disappointed to find it closed, is the fact that here we have to fill in a noun. Who was disappointed? I or friend or money or bank. So, this is the question to be resolved, and we have to appropriately fill this blank, which is a case of lexical loss. There is an element lexical item which is missing from here, and we have to fill it in there. Now, one might come back and say putting money or bank there would be nonsense. How can money or bank take this slot? Money or bank cannot be disappointed. But remember that we are talking about natural language processing, we are talking about a machine being able to process textual information, and it is possible that the machine is not endowed with common sense. The fact that money cannot be disappointed or bank cannot be disappointed comes from the fact that these words denote entities which are inanimate and are therefore incapable of being disappointed. Okay. So, therefore, that leaves us with I and friend, and both of them can qualify for being disappointed, and we have to put it here appropriately. So, how it is resolved is a different concern, but the main point I am making here is that there is an uncertainty here about which entity should fill this slot. Then we come to scope ambiguity, which is sometimes quite subtle. So, adjectives, prepositions, conjunctions, they have scope, okay, in the sense that they apply to an extended length of text, and whichever portion of text they qualify or apply to is called the scope of these entities. Okay. For example, the sentence a red ball, I will write it down, a red ball. So, the issue of scope. So, if you have the sentence a red ball, then scope of red is the ball. Okay. But if you have a red ball with a green stripe, okay, then the word red qualifies the whole segment ball with a green stripe. So, the scope in this case is a ball with a green stripe. Okay. So, this shows that an adjective need not qualify only the next noun on the surface, but it could qualify a completely large phrase. Okay. So, that is where the question of scope comes. What is the scope of this adjective? So, when we look at the issue of scope ambiguity, I find that adjective, preposition, conjunction, all of them can have scope, and therefore, in this particular sentence which we are discussing, what is the scope of with? I went with my friend to the bank to withdraw some money. So, here the scope of with is my friend, but see that a machine can get confused. Why won't it take this complete phrase, my friend to the bank, as the entity to be qualified? For example, with my friend of the yesteryears, here my friend of yesteryears can be completely within the scope of with. Okay. So, that ambiguity can arise. Next, we have this uncertainty with respect to co-referencing or anaphora as it is called. We have a pronoun it. I went with my bank with my friend to the bank to withdraw some money, but was disappointed to find it closed. So, what is this it? Disappointed to find it closed. It refers to bank. Okay, our common sense tells us that it refers to bank, but it could as well refer to money. In absence of any other knowledge, a machine could bind it to money. So, there are multiple possibilities of binding this pronoun to the noun, a task which is called anaphora, and anaphora ambiguity can arise very much in the process of text information gathering. Okay. So, this is called co-referencing anaphora ambiguity. We can now look at all the uncertainties in situation 1, which is the sentence under discussion, and we can layer these uncertainties or ambiguities. So, first level of ambiguity is at the part of speech. Bank can be noun or verb, closed can be verb or adjective. So, this layer is the layer of pause ambiguity. The next layer is the layer of sense ambiguity. Bank can be a financial institution or it could be the river bank. Withdraw can be take away or to go away. In this particular case, it is take away and bank is financial institution. Pronoun dropping is happening. So, the sentence segment is but was disappointed. So, here we place I. Scope ambiguity is the next layer, which is with my friend, and my friend is in the scope of with. The co-referencing layer, it gets bound to bank. Now, a question that arises is that are these layers arranged really this way? Is it true that we first do part of speech disambiguation, then do sense disambiguation, then resolve all pronoun drops, then solve the scopes and then bind the co-references? Is it true that we operate this way? The answer to this is nobody knows, an answer to this very fundamental cognitive question of language processing. However, when we are building a machine right now, our thinking, algorithm design etc., are limited by, but are also facilitated by this kind of separation of concerns. So, in science and technology, or the hallmark of science and technology is separation of concerns, and we have separated the concerns of language processing into these levels, which are once again part of speech tag, sense processing, pronoun dropping, scope and co-referencing. However, we can make one remark about the sequences. At least a few levels have a sequencing amongst themselves. For example, it is convenient to do part of speech tagging first and then proceed to do sense tagging, because once you have decided that this bank cannot be a verb, I need not be concerned about its verb senses. Okay. So, that is convenient, and then I concentrate only on the noun senses and then disambiguate and isolate a particular sense. Similarly, co-referencing comes pretty late, because co-referencing often is a discourse processing task where we take an element of text and bind it with another element of text which is within the same clause or outside the same clause, or even it is outside the text, and even it could be far away from the particular sentence which is being processed. Okay. So, these are the layers. Okay. Now, if you come to think of these a little deeply, we find that these are the reasons why probabilistic framework is needed to process textual information to do natural language processing. Okay. So, we record these observations. Many intelligence tasks are sequence leveling tasks. For example, to understand a sentence, maybe mechanically we produce the labels on the words of the sentence in terms of their part of speech, in terms of their sense, in terms of the co-references they should be resolved for, and so on and so forth. So, many intelligent tasks are actually sequence leveling tasks. It applies to many other branches of artificial intelligence. Then it is found to be convenient to carry out the tasks in layers. Whether human beings do it completely or partially is not completely known, but machines as they stand now have to carry out these tasks in layers. Within a layer, there are limited windows of information. Okay. The processing can happen only taking a small window and then doing the task of producing the labels. These windows provide the clues for various uncertainty resolution. And since the window of information is necessarily limited, it calls for strategies for dealing with uncertainty, because the information is never complete. And it is here that probability and Markov processes give us a way of carrying out these tasks. So, I suppose the motivation for using probability and using Markov models is clear now. It namely that we have to deal with uncertain information, and which arises because we process information in a layer within a small window. All right. So, with this background and perspective, which is absolutely fundamental, we proceed to understand hidden Markov model or HMM. We take a motivating example, which is very well known in most of the tutorials on hidden Markov model, textbooks discussing Markov model. One finds examples of this kind or some variations of this example. The example, I believe, first appeared in Rabiner's celebrated tutorial paper on hidden Markov model. So, here we have these three urns, urn 1, urn 2 and urn 3, and we are given the number of red balls, green balls and blue balls in these urns. Okay. In urn 1, we have 30 red balls, 50 green balls and 20 blue balls. In urn 2, we have 10 red balls, 40 green balls and 50 blue balls. In urn 3, we have 60 red balls, 10 green balls and 30 blue balls. Okay. And there is a person who is picking out balls from these urns, and he gives us a sequence of the drawing of balls and their colors. So, we find that the person has first drawn a red ball, then another red ball, then a green ball, then a green ball, then a blue ball, then a red ball, then a green ball and then finally, a red ball. So, this is the way the balls have been drawn. So, now the question that we are asking is, what is the state sequence, or in other words, what is the sequence of urns from which he has drawn the balls. All right. So, for this sequence of colors of balls, we have to produce urn sequences U1, U2, U3 and so on. Some UI should be assigned to each of these alphabets denoting the color of the ball. But we are not completely in dark, though we do not know everything. Okay. We still know that the following probabilities exist. Okay. If a person is drawing a ball from urn 1, Next time he can draw a ball from any of the 3 urns, and they have these probabilities. So, from urn U1, the probability of drawing the next ball from urn 1 again is 0.1, and he can draw from urn 2 with probability 0.4, and the probability of drawing from urn 3 is 0.5. Okay. So, so this is the meaning of the probability. In each cell, the column is the next state or the next urn, and the row is the current state or urn. So, if the current urn, the meaning of this cell for example, is that if the current urn is U2, then the probability of the next draw being from urn 2 again is 0.2, okay, and so on and so forth. And since we know the number of balls and their colors and the distribution of balls with their colors in the urns, we know the probability of drawing these colors also. We had 30 red balls and 50 green balls and 20 blue balls in urn 1, which gives rise to the probability of drawing a red ball from urn 1 as 0.3, probability of drawing a green ball from urn 1 as 0.5, probability of drawing a blue ball from urn 1 as 0.2. Okay. So, this is the way it is recorded. In urn 3, the probability of drawing a red ball is 0.6, probability of drawing a green ball is 0.1, probability of drawing a blue ball is 0.3. Okay. So, these two things are known. Now, the first table is technically known as the transition probability table. If we look upon the colors of the balls drawn as observations, then the sequence of urns from which they came is called the state sequence. So, this is the transition probability table, where we show the probability of going from one state to another or one urn to another, and this is called the output probability table. Okay. So, transition probability table and observation probability table. Okay. So, using these two, what is the most probable urn sequence that the person has visited? Can we compute this? This is the question. Okay. This, however, is not easily computable, and this is the observations. The states are not shown to us, and the states are, so to say, hidden from us. We have to guess at the states, albeit very systematically using the probability from these observations. So, this is the diagram which shows the situation under discussion. So, urn 1, from urn 1 we can go to urn 2 with a probability of 0.4, we can remain in urn 1 with a probability 0.1, we can go to urn 3 with a probability 0.5. So, this is the way the probability is organized of the urns. They are transitions, and the way they remain in the same state or go to a different state. Out of these states, again we will have red, blue and green coming out with different probabilities. Introducing a bit of notation here, we have the set of states as U1, U2 and U3, and V is the set of outputs, which is R, G and B. The observation sequence is O1 to up to On, and the state sequence is Q1 up to Qn. And there is a notion of initial probability pi I, which is probability of Q1. What is the probability that the system starts in the initial state U1? Okay. Typically, this is taken as 1, and this is the transition probability table, the observation probability table. Now, we discuss the question of how we can obtain the state sequence from an observation sequence. For this, we have simplified the problem a bit. We are taking another automaton, an automaton with probabilities assigned on them, and here we show an automaton with two states S1 and S2. The outputs from S1 and S2 are the symbols A1 and A2. So, we can look upon this as a 2 urn problem. S1 and S2 are 2 urns, and suppose there are only 2 kinds of balls, red and green, and A1 and A2 correspond to red and green balls. So, S1 can remain in state S1 with an output of A1 with the probability 0.1. S1 can remain in S1 state with an output of A2 with a probability 0.2. S1 can go to S2 outputting A1 with a probability of 0.3. S1 can go to S2 with output A2 with a probability of 0.4. S2 can remain in S2 with output A1 with a probability of 0.3. S2 can remain in S2 with output of A2 with a probability 0.2. S2 can go to S1 with an output of A1 with a probability of 0.2, and S2 can go to S1 with output A2 with a probability of 0.3. So, given this automaton where the probabilities of the outputs and the probabilities of transitions which are sort of merged together, okay, for such a finite state machine, how can we compute the state sequence probability given the observation sequence? So, this is a simplified problem, and you would have possibly noted also that this is a slightly different problem than the problem we have discussed with urn, where the transition probability and the observation probability were separated in 2 different tables. Here we are talking about a transition into a state and the output being produced together with their probability. Okay. So, in this situation also, how do we compute the best possible state sequence in the sense of having the highest probability? So, it is done in the following way. Suppose we are at the start state and assume that the start state is always S1. So, this transition here 1.0 shows that at the starting the state is S1 with probability 1, the other state does not exist now S2, okay. And this is with epsilon transition, that means no input has been consumed. Okay. So, now we have this S1. So, effectively this part of the tree is of interest. Now, we get S1 and this is the state. Now, we have got the symbol A1. We will be given a complete sequence A1, A2, A2, A1 and so on, and we have to get the best possible state sequence. So, here from S1 on A1 we can go to S1 or we can go to S2, that is we can remain in S1 or we can go to S2. Now, the probability of going from S1 to S1 with output A1, that probability we see from the diagram is 0.1. So, that is recorded here. Okay. So, the probability is multiplied here. This is the probability of the sequence S1 S1, which is 1.0 into 0.1 0.1, and here it is 0.3. So, the probability of this sequence S1 S2 is 1 into 0.3, which is 0.3. Now, we take the next symbol, which is A2, and when we have seen A2, S1 on A2 can go to S2 with probability 0.4, or it can continue to remain in the state S1 itself, and that probability is 0.2. Now, if we take the product of probabilities, why are we taking the product of probabilities? We will see that very soon. Then the probability of this sequence S1 S1 S1, which is recorded here, is 0.1 into 0.2, which is 0.02. The sequence S1, S1, S2, the sequence probability will be 0.1 into 0.4, which is 0.04. From S2, I can go to S1 with probability 0.3, and this is giving rise to the probability here as 0.3 into 0.3, which is 0.09. So, the probability of the sequence S1, S2, S1 is 0.09. Similarly, the probability of the sequence S1, S2, S2 is 0.3 into 0.2, which is 0.06. All right. So, we have computed the probabilities at the leaf levels. We must understand that the leaf probabilities are the probabilities of the accumulated sequences. Now, here comes the issue of Markov assumption. The Markov assumption kicks in at this stage, and we immensely save on computation. The computation becomes much more efficient than it would have been otherwise. Otherwise means without the assumption of a Markov process. What is happening here is that we find that having consumed epsilon A1 A2, okay, or having produced this sequence epsilon A1 A2, the machine can be in state S1 S2 or S1 S2 as shown here in this branch of the tree or in this branch of the tree. Okay. So, the question is, out of these 4 leaves, which leaves should we keep in under consideration, which are the leaves which should remain alive for further processing. So, the decision is made as follows: look at all those leaves which are same states. So, here S1 is a leaf here, similarly S1 is a leaf here. Of course, the backup sequence is different. Here the sequence is S1, S2, S1, here it is S1, S1, S1. So, these 2 leaves are compared, they are because they end in the same state, and out of these whichever has higher probability is retained. That means, on the next symbol, this is the state which will be advanced just like its predecessor. We will have 2 arcs coming out, we will have 2 arcs coming out with S1 and S2. And similarly, out of these 2 leaves which are both ending in S2, we will keep this S2 alive and not the other one. This particular state will survive, this S2 will survive, there are ticks here. Similarly, S1 will survive here. So, this is because the probability here is 0.09, which is much more than 0.02, and this is probability 0.06, much more than 0.04, and therefore, these are the 2 states which will survive. Now, these 2 states are completely discarded from consideration, they will not be developed further, we will not give new states to them and new transitions, we will advance these. Okay. So, this is the way the computational will produce, and whichever leaf has the highest probability will give us the most probable state sequence. So, this is a very simple idea, we keep on taking product of probabilities and keep on letting those leaves survive which are the best amongst their peers. That means, all of them are having the same leaf state. So, when we do so, we achieve an immense amount of efficiency in computation, as we will see. Now, the question that arises is, what is the rationale behind letting these survive and not the other 2? Okay. What is the reason for that? The reason is that we have made here an assumption. The assumption is that any state is the probability of reaching any state depends only on the previous state the machine was in. Okay. So, now you see the machine was in S2 before reaching these 2 states, the machine was in S1 before reaching these 2 states. Now, if we advance all these states the way we are computing, namely taking the probabilities, this effectively means that we are giving importance to calculate the probability at a leaf only to the previous state. Okay. This probability here is the accumulated probability coming from S2, and since S1's influence is absorbed in S2, we need not worry about what is happening in S1, that has been accounted for. So, later when we advance the states from these two states, these two states will have no chance of winning. Okay. Nothing, no children coming from these will ever be winners. Okay. And that is because we are always giving importance to the previous state. So, that this S2 is winner compared to this S2, and all its children will remain winner compared to all the children coming from S2. So, there is no point advancing S2 anymore. Similarly, S1's children will continue to remain winner compared to the children from this S1, and there is no point advancing this S1. So, this is due to a very important assumption called the Markov assumption. Okay. So, this is order 1 Markov assumption. We are saying that a state's behavior depends completely on the previous state it was in. Okay. So, let me write this term Markov assumption. The probability of a state being reached, the probability of a state being the state of the machine depends only on the previous state. So, this is the Markov assumption. This is order 1 Markov assumption, is order 1. All right. So, similarly we can have order k Markov assumption, where a state depends on previous k states. All right. So, in this case we have to take previous k states into account. All right. So, proceeding further, the tree structure as you see is continued here. Our sequence of observations were A1, A2, then again A1, A2. So, we got the surviving states as S1 and S2 from the right side of the tree, and this is the next state is A1. On A1 output, S1 can go to the state S1 with probability 0.1. The accumulated probability was 0.09 multiplied by 0.1, this gives me 0.009, and S1 can go to S2 with output A1 with probability 0.3. So, the probability at S2 becomes 0.027. Similarly, on this part of the tree from S2 to S1 we have the probability 0.2, which when multiplied with 0.06 give me 0.012. Similarly, here at S2 we get the probability 0.06 into 0.3, which is 0.018. So, again by using the Markov assumption, we look at these leaves S1, S2, S1, S2, and we find that this S1 is bigger than this S1. So, this survives, this S2 is bigger than this S2. So, this survives, and then after that these two states are advanced. The next symbol which is produced is A2. Now, A2 says that S2 can output A2 and go to state S1 with probability 0.3. And again by multiplying the probabilities, the probability at this leaf level is 0.0081. The probability at S2 here is 0.0054, the probability here is 0.0024, the probability here is 0.004 Okay. So, A1, A2, A1, A2 being the output sequence, we know that the most probable or the best possible state sequence would be going backward S1, S2, S1, S1, S2, S1, then S2 and then S1. So, the state sequence is S1, S2, S1, S2, S2, S2 and then again S1. Okay. So, this is the best possible most probable state sequence. And the problem which is being addressed by this tree is what is the best possible sequence S star, where we do an argmax based computation of S with the probability of, we compute the argmax of probability of S given A1, A2, A1, A2 as the output sequence and the machine mu. Okay. So, this is the probability we would like to calculate. Now, one can mathematically see why this works after we have discussed this state sequence. The system is initially, the machine is initially in S1, on A1 it go to S2, then on A2 it goes to S1 again, on A1 it goes to S2, then on A2 it goes to S1. So, the states alternate and this is the best possible state sequence. And our task, as we have stated, is to find out the best possible state sequence S star given the observation sequence O and the machine mu. The machine mu is actually the set of probability values and this argmax is over all possible S's. So, a very simple mathematics will show us that Markov assumption is indeed sound as we write down now. So, if I take this particular problem we are handling. So, S star is argmax S P S given A1, A2, A1, A2 and the machine mu. So, this will be equal to probability of let us say S I1, S I2, S I3, S I4, S I5 given A1, A2, A1, A2. So, we will neglect mu for the moment, and by applying by chain rule we have this is equal to P S I1 into P S I2 given S I1 into P S I3 given S I1 S I2 and so on. Okay. Then when we make Markov assumption, this will be equal to P S I1 into P S I2 given S I1 into P S I3 given S I2 and so on. This will continue in the next class.